Hola, good morning. The subject of my presentation is online Ramsey numbers for some graphs, and I would like to introduce what it is and what we know about this special kind of Ramsey numbers. Online Ramsey numbers was introduced independently by Beck 1993 and Kurek and Ruciński 2005. We consider the following game between builder and painter played on a large set of vertices. In each round, builder joins two non-adjacent vertices by an edge, and painter color it red or blue. Builder's goal is to force painter to create a monochromatic copy of a fixed graph H in as few rounds as possible. Painter, of course, will try to resist doing it for as long as possible. The online Ramsey number, denoted by R with a tilde of H of a graph H, is the minimum number of rounds in which builder achieves his goal, assuming both players play perfectly. It means play as best as they can play at the moment. And we have asymmetric version of online Ramsey numbers. The online Ramsey number of GH is the minimum number of rounds in which builder will force painter to create a red copy of G or a blue copy of H. Assume both play perfectly. For example, we consider P3 game where the builder wants to get a blue copy of path of length 3 or a red copy of path of length 3. We also will answer the question of value of online Ramsey number P3. In the first round, builder joins the vertices by an edge, like that, and painter color it red. In the second round, builder joins two vertices like that, and painter must color it blue. Otherwise, builder wins. In the third round, builder connects two vertices so that the painter will paint the edge anyway, red or blue, the builder wins. So, the online Ramsey number P3 is equal to 3. We only know a few values of online Ramsey number. 2005, Kurek and Ruciński prove that online Ramsey numbers K3 and C3 is equal to 8. 2014, Cymant and Gido proved that online Ramsey number C4 is equal to 10. Gryczuk-Kierstad-Prałat 2008 proof that online Ramsey number Pn is equal to 2n minus 3 for n is equal to 2 or 3 or 4 or 5. Online Ramsey number P6 is equal to 10, P7 is equal to 12, P8 is equal to 15, P8 is equal to 17. The values for path of length at most 9 and asymmetric version are also determined. The known values of asymmetric version are presented in this table. For example, online Ramsey number P6, P4 is equal to 8, or only Ramsey number P9 is equal to 17. In 2015, Cyman, Gido, Lapińska and Law prove that for all n at least 2, only Ramsey number P3 Pn is equal to this value. Cyman, Gido 2014 proved that only Ramsey number P3C3 and P3C4 is equal to 6. 2008, Gretschuk et al. Prove this chain of inequality, and by this property, and when P3 is equal to S2, that means star 2, we have that for all n at least 3, that only Ramsey number P3Cn is between this value. Cyman, Gido, Lapińska and Law also prove that only Ramsey number P3Cn is equal to this value for n at least 5. They also prove this chain of inequality. We have conjecture, and we have these two inequality for only Ramsey number P4PWL and P4PL. In 2019, we prove that only Ramsey number P4P10 is equal to 13. On this picture, we have all possible final structure in this strategy for online Ramsey P4P5 game. We use this our proof. Next, we consider lemma. Suppose Q is a non-trivial blue path with endpoints A and B. Then builder can force painter to construct either a red P4 or a blue path of length A plus 1 in at most 3 moves. This lemma is useful in our proof of theory that only Ramsey number P4P11 is equal to 15. On this picture, we have all possible final structure in the strategy for only Ramsey number P4P11 game. We use this in our proof. And for this inequality, we obtain new upper bounds for only Ramsey number P4PL, where L is between 12 and 22. For example, old upper bound for only Ramsey number P4P14 was 28, new upper bound is 21. Now we consider definition. Let F be a family of graphs and let R be an F-free graphs. We say that an HA is RF forcible if R plus 1 is not F-free. Graph H is RF forcible if there exists H prime, which H prime is isomorphic to H, such that every HA is RF forcible. We call H prime an RF forced copy H. And second definition, let F be family of graphs and let H be a graph. We say a graph R is an F scaffolding for H if the following properties hold. First, R is F-free. Second, H is RF forcible. Third, R contains no isolated vertices. 2015, Cymancido-Lapinska's law proved this inequality. And by this we immediately have that every C3 and C4 scaffolding for pk has at least k minus 1 edges. For k at least 3, every C3 scaffolding for pk has at least k edges. And 2019, for k at least 3, we prove that only Ramsey number C3 पैकी at least 2k minus 1 from fact that for k equal to 5 or 6 or 7, every C4 scaffolding for pk has at least k edges. We have that only Ramsey number C4 pk for k equal to 5 or 6 or 7 is more than 2k minus 1. For k at least 8, we have that only Ramsey number C4 pk at least 2k minus 2. In 2015, Cymancido-Lapinska's law proved this chain of inequality. Used these two lemma. Lemma that for Lk at least 2, only Ramsey number C4 PL plus K less than only Ramsey number C4 PL plus only Ramsey number C4 PK plus 4, and consider lemma let Q be a non-trivial blue path with endpoints A and B, where B is incident to a red H BC and C is not offset vertices of Q, then builder can force painter to construct one of the following structures independent of painter's choice in at most 3 runs. A blue path Q prime of length A plus 1 with one endpoint B prime, incident to a red edge B prime C prime, where C prime not in vertices of Q prime, or arret C4. And we have that only Ramsey number C4 K for K at least 6 is less than 3K minus 5. We also prove that only Ramsey number C4P5 is equal to 9, and that this chain of inequality holds. From this, on this table, we have new boundaries for the number C4PK, where K is between 6 and 10. Thank you.